Now we're on 17.4, potential, free energy, and equilibrium. Here we're going to explain the relations between potential, free energy change, and equilibrium constants, perform calculations involving the relations between cell potentials, free energy changes, and equilibrium, and use the Nernst equation to determine cell potentials under non-standard conditions. So, like we talked about in the last section, if the standard cell potential of a redox reaction is positive, this reaction is spontaneous at standard conditions. So this is why your potential for your cell, for a galvanic cell, is always positive, because you're going from lower potential to higher potential in all of these. These are spontaneous processes. We're not adding any external factor to make them go in the reverse. So if you have a standard potential of a redox reaction be negative, then this is a non-spontaneous process at standard conditions. So spontaneity should hopefully be making us think about Gibbs free energy and K, our equilibrium constant. These are all measures of reaction spontaneity. It's spontaneous if we have a positive potential, a negative delta G, or a K greater than 1. And we're going to talk about the equations that relate these variables. So let's first talk about potential and Gibbs free energy. So delta G standard is equal to negative N times F times E of the cell. So we have the standard conditions, which is that 1 atm for our gases, 1 molar aqueous species, delta G being the standard free energy change from last chapter. E naught of the cell is the standard cell potential. N is the number of moles of electrons that are transferred in the balanced redox reaction. So you need to make sure that the reaction is balanced and then go, okay, look, I see 3 electrons that are being transferred. Okay, so N would be 3, for instance. F is called the Faraday constant, and this is the charge of 1 mole of electrons. So Faraday's constant, F, is equal to 9.648 times 10 to the 4th joules per mole volt. Kind of weird units, I know. But one thing you should notice is that delta G and E have opposite signs. So delta G is negative in order to be spontaneous, but the cell potential is positive. Now, our redox reactions, just like all reactions, eventually reach a state of equilibrium. So equilibrium never leaves us. And so the potential for the cell is equal to RT over NF times the natural log of K. I know you guys are probably super excited to see K back. I'm sure you are. And then just remember that E of the cell is also oh, never mind, sorry. Okay. We could also use this in terms of delta G. So remember that delta G naught is equal to negative RT times the natural log of K. And we also just established that delta G is equal to negative NF E cell. So this is where this equation was derived. So then divide both sides by NF, or negative NF, so that's what gets rid of those negative signs. So then you get that RT over NF times the natural log of K is equal to the potential of your cell. So just so you can see where that equation is derived. So when these experiments are done at 25 degrees C or 298 Kelvin, RT over F is basically just three standard values. These are 3 constants. So you can just combine the 3 of them and use 0.0257 volts. And so then the potential for the cell reduces to 0.0257 volts over N for the number of electrons, or moles of electrons times the natural log of K. Only at 25 degrees Celsius, though. Keep that in mind. If you are at a different temperature, then your T in this term is going to change. So if your cell potential is positive, your K is greater than 1. If your potential is negative, K is less than 1. So your book gives you this really cool graph kind of showing you the relation between these three processes. If you want to just look at delta G and E, you use the bottom one. If you're looking at delta G and K, you use this left one. And if you're looking at K and E, you use the far right one. So it's just kind of a nice way to see everything related and be able to pick out what you need to solve for. So let's look at an example. We want to use the data from Appendix L to calculate the standard cell potential, standard free energy change, and equilibrium constant for the following reaction at 25 degrees Celsius. We want to comment on the spontaneity of the forward reaction and the composition of an equilibrium mixture of reactants and products. All right, so to get our standard cell potential, we need to use that Appendix L data since we have a nice redox reaction. So our anode, we have iron going to iron 2+, since our anode is where our oxidation is happening. So that is Fe solid going to Fe2+, and that means it's making 2 electrons. And this potential here, I'm just going to call this EO, for oxidation, is equal to negative 0.447 volts. So then our cathode, which is where reduction is happening, we have 2, since there's that balance 2, times the whole thing, which is Ag plus aqueous plus an electron going to Ag solid. And so this potential is equal to 0.7996 volts. Let's write this a little prettier. That looks better. So the potential for our cell then is cathode minus anode, and that gives us a positive 1.247 volts. Check something really quick. Appendix L is very big. It has lots of reactions, but it's mostly alphabetical order. So that does help a little bit. Okay, so when you're doing this too, even though the amount of silver, there's 2 silvers, you don't have to double the potential. You can just leave the potential as it is. That's why the 2 times the reaction is just kind of on the outside. But the biggest thing here is this shows us that it's 2 electrons being transferred. So that means N is equal to 2. And then we know our potential of the cell as well. So since we're looking at equilibrium, we want to go ahead and calculate K. So we know E cell is equal, since it's at 25 degrees Celsius, we can use our little 0.0592 volts over N times the log of K. So then K is going to be equal to 10 to the N times our potential of our cell divided by 0.0592 volts. So this is 10 to the 2 times 0, oops, not 0, sorry, 2 times 1.247 volts divided by 0.0592 volts. So we can see our volts there cancel, which makes sense because 10 to any power, there shouldn't be any units. So good. So then this becomes 1.3 times 10 to the 42nd power. Yeah, I'd say that's a little bit greater than 1. What about you? So then the standard Gibbs free energy, we can also calculate, is equal to negative NFE of the cell. So this is negative 2 times Faraday's constant 96,485. The other way of writing Faraday's constant is coulombs per mole, C over mole, times the potential for the cell, which is 1.247, and a volt. A volt, by the way, is equal to a joule per coulomb. So this is joules over coulombs, so you can see the coulombs cancel out. And then this becomes negative 240,600 joules per mole, or if we want to make this kilojoules, 240.6 kilojoules per mole. Whoops, negative. So delta G is negative. Okay, the reaction is spontaneous, which we can tell just by the potential of the cell being positive, delta G being negative, and K being freaking huge. So this reaction is going to go to basically completion to give us an equilibrium mixture. Because of how big K is, that's why we want to look at K. The bigger K is, the more towards the product side. And because K is so big, this tells us that our equilibrium mixture is going to be mostly products. It's very much favoring the forward reaction. So now let's talk about non-standard conditions. So let's first look at concentration. So far we've only talked about standard potentials, which is when our gases are at 1 atm or 1 bar, they're basically the same thing. And if we have an aqueous species, it's a concentration of 1 molar. Now our reaction conditions greatly influence our Gibbs free energy, so our potential for our cell must also be influenced by these conditions. So we can make a concentration cell by connecting two nearly identical half cells, each that has basically the same half reaction, use the same electrode, but the only thing that changes is the concentration of one of the redox species. And the potential of that cell is actually determined by the difference in the concentration of the species. So the voltage of our system is going to increase, and a reaction will become more spontaneous if we increase the concentration of a reactant or we decrease the concentration of a product. Think Le Chatelier's principle. Okay, when you're increasing a reactant, you're going to push that reaction forward, so you're going to increase the voltage because there's more transfer happening. We're going to decrease the voltage and become less spontaneous if we decrease the concentration of a reactant or increase the concentration of product. So Le Chatelier's principle never leaves us. So this brings us to the Nernst equation. I've always just kind of laughed about just the name Nernst. I don't know, it just makes me chuckle. So this tells us that the potential for a cell is equal to the standard potential minus RT over NF times the natural log of Q. Q's back! So we saw K, and now of course we have Q. So if we're at 25 degrees Celsius at 298 K, we can change that RT over F into a nice number for negative 0.0592 volts. So let's go ahead and predict the spontaneity of a reaction with non-standard conditions. So we're told to use the Nernst equation to predict the spontaneity of the redox reaction shown below. Oops. Okay, so we're going to have to use Appendix L as well. The nice thing is we're already given our overall reaction, so we know what to look for in the appendix. So cobalt here is being oxidized. It's going up in oxidation number. So this is going to be our anode. So we see solid cobalt going to CO2 plus aqueous plus 2 electrons. And the standard potential for this guy is equal to negative 0.28 volts. So that means that our other half reaction is going to be our reduction at our cathode, which is the iron 2 plus. And 2 electrons going to solid iron. And its potential here, standard potential, is equal to negative 0.3 0.447 volts. So that means the standard potential of our cell is equal to cathode minus anode. So that is negative 0.447 minus negative 0.28. And that gives us negative 0.17 volts. So this is not a spontaneous process under standard conditions. So we can't say it's non-spontaneous under the conditions we're working with, though, because the concentrations can change that. But if this were under standard conditions, it would be non-spontaneous. So now we need to go ahead and use our Nernst equation. But we can go ahead and look at Q. So if you remember, good old Q is equal to your concentration of your aqueous products over your aqueous reactants. So in this case, the cobalt 2 plus is our product. That's 0.15 molar over reactant of 1.94 molar. And so that is 0.077 for Q. So then the potential of our cell is equal to the standard potential minus 0.0592 volts over N, which in this case N is equal to 2. We can see those 2 electrons times the log of Q. So then plugging and chugging, we have negative 0.17 volts for the potential of the cell minus 0.0592 volts over 2 times the log of 0.077. And when all this is said and done, we get negative 0.014 volts. So we still have a negative cell potential, very slightly negative, but still negative. So this would be a non-spontaneous process. So let's look at another example. Sorry, I kind of skipped. I did talk about concentration cells already. Never mind. Okay, so this example is looking at a concentration cell, and we want to know the cell potential of it, described by this cell notation given here. So we can use this information to write our half reactions for the anode and the cathode. So at the anode, we have zinc solid going to zinc 2 plus. And we can just remind ourselves this is aqueous and 0.10 molar. And so that we know that there has to be 2 electrons that are transferred here. And at our cathode, we have zinc 2 plus, and this guy is aqueous, but at 0.50 molar. And 2 electrons going to solid zinc. And for both these half reactions, the standard potential is equal to negative 0.7618 volts. So then the overall reaction is zinc 2 plus, aqueous at 0.50 molar, going to zinc 2 plus, aqueous at 0.10 molar. So now we can go ahead and use our Nernst equation. So let me just rewrite. We have the potential for our anode is negative 0.7618, and so is it for our cathode. So then the standard of our cell, potential of our cell, is equal to 0. So now going to the Nernst equation, the potential for our cell then is equal to the standard potential, which is 0, minus 0.0592 volts, since we're just going to go ahead and use 25 degrees Celsius. It doesn't say not to, so that's what we're going to do. Divided by 2, so N is 2 here, you can tell by the 2 electrons, times the log of Q, and so our product side is 0.10 divided by 0.50 from our reactants. And this gives us positive 0.021 volts. So this would tell us that this overall cell reaction is spontaneous. So this reaction has the zinc ion concentration in the cathode falling. It's being reduced to elemental zinc, while the anode side is rising. So it's being produced by the zinc anode.